In 16.1, we're going to learn how to solve a particular type of first-order differential equation. Last year and in the previous video, we looked at an equation like this, where we solved something that was a first-order differential equation. It wasn't exactly in the same form. We could get it in the same form, but we solved something where it was possible to separate the variables. So all the x's together and y's together. In this case, we're not necessarily able to do that, but when we have an equation in the form of m dx plus n dy is equal to 0, this alone doesn't make it exact, but if we have something in this form, it's considered to be exact, and the entire equation is considered to be exact, if there exists a function in f of xy with constant partial derivatives of fx and fy. So I'll say with, not constant, but continuous partial derivatives fx and fy, where fx is your m, which is a function of xy from up here, m. Your fy is at n of xy. Okay. And if this is true, so it's exact if there exists this, and also the solution to the differential equation is f of xy, so whatever that function is equal to c. Now this might look very familiar, because this looks a lot like when we had a line integral of f dotted with dr, where your vector field was, if it was in 2 dimensions, mn, and then your dr, you dotted with that with the dx dt and a dy dt, and when you do this, you end up with the integral of m dx plus n dy, and if it's a conservative vector field, if f mn is a conservative vector field, then you can find your potential function f of xy, which is really the same thing we're doing here, even though this isn't a line integral, it's just a differential equation. But we do these steps the same way, and it turns out that the solution to our differential equation is that function equal to a constant. Remember, you don't just get one answer when you solve a differential equation. You get something like this. This one here. We got an entire family of equations where c can be any constant. Any equation in this form will be a solution to this differential equation. You get a family of equations. So this is going to be your family of equations. That's the solution. Okay? So let's try an example. So I have something like 2xy minus 3x squared dx plus x squared minus 2y dy equal to 0. First, I want to know, is this thing exact? Second, if it is exact, I want to find that function f so that I can find the solution to this differential equation. Okay? If you notice here, this might be a lot more difficult to separate your variables like we did the example from the previous day, or like you did last year. Okay? So this thing is your m, this thing is your n. Let's find m dy, which is equal to 2x plus 0. Let's find dn dx, which is 2x. Okay. What we're doing here is basically figuring out, like we did in chapter 15, if there exists this function. The way we figure out if there is this function is we find, basically we're asking the question, does the partial m with respect to y equal the partial of n with respect to x? Okay, so it's the same test to see if something is conservative. It's really a test to see if there exists a function such that this is true. Okay? Because if this m is a function of x, is a partial of x for some potential function, and this n is a y partial, well, if we take the y derivative of this and the x derivative of this, then we have an fxy and an fyx, and if those are equal, okay, then we know that this function does exist. Okay? We know that taking these derivatives will ensure this function exists. Okay, so let's go down here and continue this. This is exact, so since this is exact, we basically have to find this potential function and set it equal to our constant. Okay. So if this is true, we know that this m, like we set up here, this m is an x derivative of some potential function, and this n is a y derivative of some potential function. So this thing is a fx, and this thing is a fy for some potential function. So we're going to say fx is equal to 2xy minus 3x squared. Take the antiderivative with respect to x, so let's call it f of xy. That's going to be our function we're looking for right here, is equal to, the antiderivative with respect to x is going to be x squared y minus x cubed, and then plus some function of y. Since it's an x partial, there could be some y's in there. Okay. Now we're going to take the y derivative of this, and we're going to compare it to this fy. So the y derivative of this is going to be x squared, that goes away, plus g prime of y. That's going to be equal to this thing, x squared minus 2y. So now we can set these equal, cancel those out. G prime of y is equal to negative 2y. G of y, taking the antiderivative with respect to y, is going to be negative y squared. Plug this back up here, and we get our function. F of xy is equal to x squared y minus x cubed minus y squared plus a constant. I'm just going to say plus k. Okay. So when we took the derivative, there should have been a plus k here. Okay, so now what we do, we're going to take this thing, which is our f of xy, and set it equal to a constant. So equal to, I'm going to call it C1. Fell off the edge. C1. Because we don't want this part in our answer. We're just setting this thing equal to a constant. So our solution, x squared y minus x cubed minus y squared. And then I can combine these two constants. So the C1 minus the k becomes a new constant, and we'll call that C. So this is your solution right here to our differential equation. It's really a family of solutions. For any constant C, we've got this equation equal to C. That's going to be a solution to this equation. And now I'm going to throw one more thing into this, because if it's not exact, sometimes we can manipulate it to make it exact. So for instance, let's say I have a fairly simple equation, 2y dx plus x dy is equal to 0. Okay, let's see if this is exact. That's our m. We want to find dm dy, which is equal to 2. This is our n. dn dx is equal to 0. Okay, they're not equal. This is not exact. But watch this. If I take this equation and I multiply both sides by x, and I think, why x? Well, bear with me for a second. But if I multiply both sides by x, 2xy dx plus x squared dy is equal to, multiply by x, we still get 0. I didn't really change this equation. I just kind of manipulated it into a different form. Now let's see if it's exact. So this thing's our m. dm dy would equal to x. And dn dx, sorry, that's an n. dn dx would be equal to 2x also. Okay, so now it's exact. And since it's exact now, we could, more like an n, since it's exact now we can use the same procedures, and we could find our potential function f, set equal to c, and that would be our solution to this differential equation. So now you're wondering, let's go back to this question, why I multiply by x. This thing's called an integrating factor. So basically what I'm doing, I'm manipulating this function by multiplying both sides of the equation by an integrating factor so that it's more easily solved. But the hard part is finding that integrating factor. Okay, so there's a theorem, 16.2, to help you find integrating factors, if they exist. And what it says, there's two parts, because you look for one or two things to happen. So if 1 over n, remember the n is this thing, if 1 over n times your y partial of m minus your x partial of n equals some function that only has x's in it, could just be constant, but only x's, no y's, then your integrating factor is e to the integral of h of x dx. Okay, you might be thinking, where the heck did all that come from? Well, I'm going to tell you, unfortunately, this is going to be presented without proof. This is a theorem that's presented. The book doesn't even go into a proof of it. I believe it's because you would need higher math courses than we have right now to actually come up with this theorem. Okay? The other one is if, it's very similar to this, but if 1 over m times nx minus my ends up being just a function, I'll call it k, of y, no x's in it, then your integrating factor is e to the integral of k of y dy. Okay? So you're looking for these two things. Now, one thing you can notice here to help you remember this, if you look at this thing, the my minus nx, this thing you're divided by, the n usually goes with x, so the n and x go together. This m, if the m's on the denominator, the m usually goes with y for your my. So that maybe that'll help you a little bit remember this theorem. Okay, so let's try an example. So an example. If I've got y squared minus x dx plus 2y dy is equal to 0. Remember, this thing's your m, this thing's your n. Okay, so what we have here is, if I want to find dm dy, that would be 2y, dn dx would be equal to 0. Okay, that doesn't work. Let's see if we can find an integrating factor. Okay, so what I'm going to do, I have to think about your dm dy, your my, and your mx up here. So if I'm going to subtract these two things, and whether I do 2y minus 0 or 0 minus 2y, I'm then going to divide by either n or m. Do you want to divide by this thing, or do I want to divide by this thing? I probably want to divide by this thing. Look at what happens. If I subtract these and divide by this, it looks like not just x or y is going to go away, they're both going to go away. Okay, so I'm going to look at this one. 1 over n times my minus nx. Okay, and if that's equal to a function of x, then this is an integrating factor. Okay, so let's try 1 over n, 1 over 2y times my, which is 2y minus 0. Okay, I just get 1. So my integrating factor is equal to e to the integral of h of x dx, or e to the integral of 1 dx, or e to the x. Okay, so I'm going to take both sides of this equation and multiply by e to the x. Now let's go to the next page. So I'm going to take y squared minus x, e to the x, dx, plus 2y e to the x, dy is equal to 0. Okay? And now I'm going to take this thing and I'm going to see if this is now exact, just to verify. It should be. So this is my m. So dm dy is equal to, take the first times the derivative of the second, plus the second times the derivative of the first. I get 2y e to the x. And then this thing is my n, so dn dx is equal to 2y e to the x. Okay, well that works out nicely. So these are equal, so this is now an exact differential equation. So I could go through the steps. X would be equal to this thing, y squared minus x e to the x. Take the antiderivative with respect to x. take the y derivative. This should be set that, compare that to this, and find your